Over the past about 3 years, AI has exploded, mostly due to large language models. And of course, one of the biggest known problems with them are hallucinations. And so language models are trained based on a corpus of data, just like any other machine learning model. And the result of that is the output of the language model is correct in a statistical sense, which is why you get hallucination. It is trying to mimic the training data. It is trying to mimic it to an extent where it's fitting a statistical distribution. Today, I'm going to talk about a different branch of artificial intelligence, where we look to conclude things from a logical perspective. So where with logic programming based methods, we generally don't rely on a large corpus of data to learn things, which makes coming up with that baseline knowledge a bit more challenging sometimes. We can be assured of correctness of the results more often than not. And the way forward, some people believe, or things like artificial general intelligence, is to take the ability to learn from data of these deep models to include LLMs and somehow couple it with the ability to be correct in the symbolic approaches. All right, so what we're going to talk about today is mostly dealing with this logic-based approach. So what makes AI systems think? Well, somehow if you infuse domain knowledge. So infusing domain knowledge is different than using training data. So if I give you, say, a set of differential equations, that is domain knowledge about your given problem. It's something that we have discovered and that we have tested out and we've evaluated rigorously. We're not just throwing data at it. How do you draw conclusions from that knowledge? Or to be able to draw conclusions from that knowledge, we do what's called multi-step inference. Now, this is another place that is really difficult for the language model. In that, if I have a machine learning model and it's trained to be, say, 99% accurate, but I'm using it in a multi-step process. So step one, 99% accurate. But step two, my accuracy is decreasing because the accuracy of the next result conditioned on everything, all the input being correct is 99%, but my input's only 99% correct. And as you do that, that error compounds. And very quickly, suddenly you start dropping to, say, 70% after like 5-6 steps. And with a logic-based approach, which is what, say, your calculators use for arithmetic, you don't worry about the propagation of errors. It just works. The propagation of errors doesn't come into play until you deal with things like numerical instability or cosmic radiation and stuff like that that's extremely rare. So you have a much higher accuracy for each step. But at the end of the day, everything being described here is the capability to reason. And so the so-called reasoning models that have been employed lately, and there's been a lot of success, they are inspired by ideas from reasoning, but they are not executing correct reasoning. What they are doing is they would be called reasoning about something. They're reasoning about the language that's coming out of the model and using that to kind of guide the language model toward a more useful solution. And I'm not saying that's a bad thing. I think it's a really important advance. And I also want to clarify, like, I don't think large language models are bad or the machine learning approaches are bad. But what I want to highlight to you as I motivate the rest of this talk is that uh, they have their limitations. And some of these limitations are fundamental. So in my research group, we started to look at a couple things that, hey, if you want to do reasoning, and there's plenty of ways to do this, what are some things that would be really important to have? Well, one, connecting logic with a deep learning or machine learning model. And we as humans do this all the time. We can read numbers in a variety of fonts, a variety of handwriting styles, and we can still interpret those numbers correctly. A machine learning model that's trained on data can get really good at this. And that can provide a useful way to what psychologists call ground a symbol in perception. And so can we connect a logical system with a machine learning one to ground these symbols in perception? Another shortcoming on the logic side is a lot of things in logic will assume if that's not true, it's false. That's called closed world reasoning. But we thought it was a better idea to think about, hey, can we allow for saying, I don't know? Can we allow for things to be uncertain? And this is not only important from sort of a philosophical perspective that you want to have this capability, but I'll show later it's important from a computational perspective. Because if I have to identify every aspect of the world and label it as true or false, it takes a lot of memory. And we as humans don't do that. We as humans start identifying things as true or false that are important to us, that are relevant to what we're trying to do. And so this, I'll show you later how that becomes important. The other thing here is a lot of methods from logic are older pieces of software. And so we wanted to do something more modern using a Python interface so you could use it more easily. So the fundamental idea was from an old paper from the early 90s called Theory of Generalized Annotated Logic. And the authors introduced this notion called a generalized annotated program or a GAP. And the main idea here is they could obtain what's called tractability in this logic, but still allow for truth value beyond true and false. And the truth values could be assigned on a mathematical structure called a lattice, and I'll give an example of what that looks like. But when I say tractable, we can execute this algorithm exactly, and it can still run on a computer and terminate. And what's more, in most cases, it's not just tractable, but it's very efficient. And so we wanted to take these ideas of efficiency and leverage them in a more modern piece of software. And in many ways, I was inspired to do this because a lot of the success of neural networks is because they started with a tractable framework. You would not get a large language model if the underlying neural network was intractable to train, or even if it was more complex to train than it is. The feed-forward architecture doesn't have any loopbacks for a reason. And it wasn't because that wasn't the powerful capability, it was because it would have caused the implementation to flow to a crawl and not scale. So we wanted to mimic that on the logic side. So that's why we use this as a baseline. So we came up with this idea called lattice annotated temporal logic, or lat logic. And here's what the lattice looks like. You have this bottom element, and as reasoning proceeds, you move up the lattice. Now we represent the elements with something that I think has an intuitive feel as a subset of the unit interval. So when you look at it, we can think of, hey, total uncertainty is 0, 1. Total falsehood would be 0, 0. Total truth would be 1, 0. You could have things like 0.61. You could think of that as like 80% plus or minus 20%. So these have kind of this intuitive feel. As we reason about things, we're closing on that bound. we're getting more confident about what that scalar value should be. We also extended annotated logic for use over time. And so with the logic, we have these rules that are just of the form, if this, then that. And there is a time lag between them. But what's key here is the time lag isn't always just, hey, in the next time step. A lot of ideas from reinforcement learning and game design are based on what's called the Markov assumption. And the Markov assumption says, hey, everything that happens in the next time step is dependent only on the prior one. And we wanted to break that by allowing, hey, some things happen faster than others. So we did some work, I'll show you in a little bit, with simulations and games. And if you have a game and you want to model a bullet hitting a target in the same environment as a vehicle moving from one place to another, they're operating on a totally different time scales, but they need to happen in the same scenario. And so this idea here was to enable that. The other thing is we want to allow total uncertainty as the default value. Because if something is totally uncertain, I don't need to represent it in memory. I assume everything is totally uncertain. So this allows me to take logic, which is designed for operating in a discrete space, and doing it in things like a continuous space. So I could say, hey, I have an infinite number of things I could care about over here, but they all are totally uncertain. But then when I do the reasoning process, and this agent, for whatever reason, moves left, I instantiate a new logical symbol right at this point. And now that symbol has a 1-1, it's true, where it wasn't before. So inference closes the gap on that bound, and it gave me a new piece of knowledge, and it did so in a memory efficient way. Just to hone some intuitions on how this works over time, another interesting byproduct of this is that even though we are closing up that bound, making things more and more certain with inference, we have separated that from the notion of time. So the way we think about this is we have everything we care about at all time, and as we do inference, we update our knowledge about that as the inference algorithm proceeds. Because we do it this way, we can have things become more true or less true over time and still maintain the tractable quality. Here's an example where we have a supply chain network. We have these P nodes that are suppliers of C1, and C1 is a component of P3. And then we have these rules. I put them in logic, but I put them in English here for you as well. If a single component of a product fails from time t to t prime, and that product node fails from time t+1 to t prime plus 1. So basically, if any of these if this component fails, it doesn't matter about the other components, this product fails. If all suppliers of a component fail, then that component fails in the next time. So if both P1 and P2 are dead, then C1 is dead, otherwise it's not. So let's just see what happens when we.
So if only P2 fails, then C1 is not dead necessarily.
Yeah, and based on this particular logic.
Right.
Yeah. So I'll walk you through an animation. So here, we're saying, okay, something happened, both these things died. So we update our inference, everything else. So you see the inference over time shown on top. Everything else is uncertain. We run inference. We use this rule fires, and it causes C1 to die. The next step, this node dies because one of its components failed. However, since then, P1 and P2 have recovered. So what happens is, as we progress, the failure kind of flows through the system, and now we can model this. But again, we've done so in a way where we've maintained the ability to actually compute it. So we created an implementation for lat logic called PyReason. And so these facts, like what you saw, those two nodes that initially failed, as well as the structure of the supply network, we allow this to be modeled as a graphical structure. And here the graph, the nodes and edges are labeled with multiple different labels, and you could have multiple different truth values and stuff. So you have this kind of rich representation. So that you have as input. And the other piece of input is these rules. Now, these rules can be manually specified if you have an expert. There are algorithms that allow you to learn these rules from data. And there's people that are doing research now that are trying to find ways to reliably create rules based on an LLM, going from natural language to PyReason can compute that inference process, and we gave it some features. And it can tell you everything you saw in the last few slides about the supply chain. It can report that to you in what we call an explainable trace. So it says, hey, this is all the inference that happened, and this was the result of each of those steps. The other interesting thing about it is you can compute aggregates over it. So if you have a certain atom that maybe represents a place on the ground, or maybe it represents kind of if you're playing a video game, like a gold coin, a character is grabbing, you can just do an aggregate over the truth values of the result of PyReason and record them. This is handy because in reinforcement learning, this allows us to train an agent to move toward a goal. So this software has been around for a couple of years now, and so we have a bunch of users and stuff. And I'm going to talk about not as much about PyReason itself, but things that we've done with it that I think might be of interest. So I lump these into two categories. So first deals with modeling agent behavior. Because lat logic is a temporal logic, it allows us to model things over time. That's very handy for thinking about an agent that's taking an action in the world and trying to predict what they're doing or generate what they're doing next. And so the three topics I'll talk about will be using this with reinforcement learning, modeling human movements, and also a maritime application. On the other side is, because we have these truth values that are dependent on the lattice, then most machine learning models will report things as sort of a conditional probability. We can write code to integrate the output of the machine learning models with PyReason and lat logic. So first we're going to talk about how this interfaces with optimization procedures, specifically for medical triage. Then we're going to look at how it interfaces with machine learning models from kind of a coding perspective. So this was a very applied paper where we looked at, hey, how can we best implement this to support a given workflow? And we'll wrap up talking about metacognition, which is metacognition deals with the idea of, hey, I have these results from a machine learning model. I know they're only true in a statistical sense. How can I sift through those results and decide which ones to take? All right, so let's go through the first batch. So this first work, semantic proxy for a course of action generation. So traditionally with deep reinforcement learning, you have some kind of simulator. So like when the Google DeepMind guys created AlphaGo, they were simulating this game over and over again. And every time the agent plays the game, that produces a reward. If won or lost the game or scored so many points. And that information goes into the deep reinforcement learning algorithm to update the agent policy. Now, a key problem here is what's called data efficiency. You need a lot of simulation runs in order to train an agent. So again, with AlphaGo, they measured this in like equivalent to hundreds of thousands of human years in gameplay to learn how to play that game. There are certain applications that have really great simulators. So think about, flight simulators or simulators for the military. Those are very high resolution simulators, and they'll run at time scales of say 1/60th of real time, 1,000th of real time. You can't use even something that's 1,000 times faster than real time in an algorithm that needs 600,000 years of gameplay.
That's 600 years.
600,000, yeah, it would take 600 years to run, is what I'm saying. So we came up with this idea that you could create what we call a semantic proxy of the simulation environment. So all a semantic proxy is just a set of those rules that is designed to mimic the environment. And so when we had two simulators we compared against, and doing this was about 1,000 times faster. The other thing we checked against was the reward earned by the agent. Was it about the same as what happened when we ran it back in the simulator? And the answer was yes. But what's interesting though is that we found the ability to capture these non-Markovian relationships gave us improved reward. So it was harder for the reinforcement learning algorithm to learn a good agent behavior policy when we enabled the non-Markovian reasoning, so allowing the multiple time steps. But sort of once it got it, you had this red line, it drastically outperforms where you make the Markovian assumption. And this makes some intuitive sense because we would think that it's a very force-strained world to only model everything that happens in the future is based on what happened in the last time step. The other thing that's interesting about it is it produces this explainable trace. So if you want to go back and look or have another algorithm that analyzes everything that went on, you have that information ready. And this is something that kind of comes up a lot in some of the other work we've done. So then the next problem we worked on was generating realistic human movement trajectories. Now, so there's a lot of interest in doing this because if you say have a disaster situation or you're preparing for a disaster situation, then you want to model where all the people are going. How do you go about doing that? Even if you have data about people's movement, you're not going to have a lot of data about people's movement in the aftermath of a disaster. But you have an idea of what they normally do. So the challenge is, hey, we want to put constraints on the movement of these simulated people, but we also want it to be realistic at the same time. So in other words, we want to learn behavior that looks realistic, but is taking a different path. So I'll give you an example. All right, let's say I really like coffee shops. And I'm in a totally new city. So I decide I'm going to look up a coffee shop that's close to my hotel I'm staying with, and I'm going to go to the coffee shop. You could imagine that would be predictable behavior, even though it would be a totally new place and you would know nothing about my behavior in that particular city. This is an area where machine learning models tend to fail because if things aren't mimicking the training data, they don't have that necessarily stored in the model. So what we did was we represented the behavior of a bunch of simulated people or agents using these logical rules. And then we set about searching throughout the search space of all possible trajectories for a given task to go from point A to point B and stopping at certain locations. But if you do this with the brute force approach, you quickly find that that's also, you run into the tractability issue. Because there's a lot of combinations of different ways you could go that may or may not be realistic, may or may not be meet the constraints. But what we're able to prove is that if you take a subset of those rules, that won't be the correct answer, but a subset of those rules dealing with that do adhere to the Markov property, that can allow us to guide the search in a way that gets rid of a bunch of bad paths. And that turns out to give us tractability. So here's without this guidance, and here is with, and so we were able to actually compute it. Running this on, I think, like 100 cores and a terabyte of RAM, you still couldn't get it to complete in certain graph sizes within 48 hours. So what's interesting about this particular program is the idea was to create, the way we were evaluating was to create movement trajectories that a machine learning anomaly detection model could not detect. And so the way this government program was structured is we had people doing that on our team who were separate from us. And there were people creating these algorithms for detection on other teams. And we were judged by how well our trajectories were detected. So basically this chart, without getting into the technical details, of 1 means that the anomaly score was the same as the historical data. So anything above 1 indicates like some small signal of being anomalous. Anything 1 or below is not high enough for any reasonable user to say that is anomalous because it's a lot like the training data. So very few things were even above 1, and they were only, so you can interpret like a 1.3 as being 30% more anomalous than data that was in history. So with one thing about that problem that was interesting to us is it got us thinking about, hey, a lot of data that we could do analytics on is in the form of a trajectory. And then we started talking to some people involved in maritime operations, and they said there's a really big problem in the maritime domain, and that is you have what's called an AIS tracking system on all these commercial vessels. And what happens is when someone that has a commercial shipping vessel, they're supposed to have the AIS system turned on at all times. And this information is available to anyone, and there's companies that provide services that you can get actually a list of all locations where any shipping vessel on the earth is at any given time. Now, when a ship captain decides to have the AIS system turned off in the middle of a voyage, what do you think that means? Why would someone do that?
Yeah, they could be involved in some illegal activities.
Exactly. Usually it's some illegal activities, like sanctions violations is the big reasons.
Or perhaps there could be a problem with the ship would be in distress.
But they wouldn't turn it off on purpose if that was the case. They would actually want it on, so they could be found. But the other reason is you may have heard of in the North Sea, cables being cut by the Scandinavian countries, by Russian vessels. those vessels would turn off their AIF system before doing that behavior. There's also lesser things like illegal fishing, which has environmental impacts. So it's a big problem. And the thing is once that AIS system turns off, how do you predict that future trajectory? So machine learning based approaches that use statistical modeling do a really great job on this to predict an hour into the future. And then they are pretty much stuck. And the reason for this, I believe, is that the machine learning models are not good at predicting multiple potential futures. And so we frame this program or frame this problem as what's called an abductive inference problem. Or what we did is we learned rules about ship behavior. We put those into PyReason, and we predicted different areas where the ship could go in the future. And so we framed this as an optimization problem. So once the rules were learned, we're looking to optimize these, essentially where these stories are based on the rules. And so what we found was looking at the amount of area that you're willing to search versus the recall, so the fraction of ships found, how doing this abduction approach with PyReason compares to state-of-the-art deep learning and a random approach. As we see, the deep learning approach really early on here actually is outperforming our method by a little bit. This is like looking at things in the very near future. But as you increase the area and want to look further into the future for where the boat could be, your performance levels off very quickly with the statistical approach because it can only get you so far. So then the next group of papers I'll discuss deal with interfacing with other systems. So let's start with the orchestrating optimization. This is another kind of wicked problem. So let's say we have a bunch of casualties. So people that got hurt hiking or, maybe in the military or law enforcement, or maybe people who survived something like a plane crash, and they're scattered in different locations. And you are charged with rescuing. You have a bunch of helicopters with pilots at your disposal. You have people with certain medical specialties. And how do you optimize for rescuing as many of these people as possible? And it turns out that in literature on medical triage, there's different ways to frame this problem. So there's looking to frame problem on, are you going to try to minimize the number of people that are imminently going to die? You're going to maximize the number of people that you can save. So maybe someone who is really far gone, but he's way over on the other side, and there's 5 people that are in a more moderate condition, you go rescue them first. How do you deal with logistical constraints? So pilots need rest. If the pilots of the helicopter don't get enough rest, they could get in an accident and be hurt. So we got to take care of that as well. So there are ways to frame this as an optimization problem. And if there was one good way to frame it as an optimization problem, you could go to any operations research major and they can solve it for you really fast. There's software for it, it's well known, you can frame it and solve it. But the problem is, how do you frame this problem? You may have also other aspects, like you might not know all the information about the casualties and so forth. So what we did here was we used logic to take the input of the situation, and we would frame multiple optimization problems. So we framed a whole bunch of optimization problems, and then the result of PyReason, the output would be optimization problems that would look something like this, that an operations researcher would be used to. Now, these are well known. Now you could solve them, like I mentioned, you could kick them off to a solver. So we designed a software workflow where those optimization problems, they all got shot out to solvers. And then the results from the solver were thrown back into the logic. So it's like, hey, inference, you wait while this other optimizer solves these problems. Now we're going to get the results back in the logic. The logic then looks through the results and based on some rules, comes up with what it recommends. And because of that, you can see it'll also have reasons why it picked one optimization solution over the other. So for example, if you were doing this, solving this problem, and I said, hey, you know, all your helicopter pilots, they really should have 8 hours sleep or there's going to be, you know, a big risk in getting in an accident. But what if you could save 2 more lives with sacrificing 10 minutes of sleep? Of course you would do that. You're not adhering to the constraints strictly, but the violation of that constraint for the outcome is very much worth it. And so, of course, we got this really nice company we work with that their business was creating simulated casualty data for use in exercises. And so we had a whole lot of data. We were able to compare this with standard baselines. And you know, we found it was very effective. They also did some work on mocking up how the results could be visualized in the user interface to support a decision. But this is one way to interface logic with a different system. Here we're interfacing it with an optimizer. But of course, as I mentioned early on, you know, one of our initial goals was to allow it to communicate with machine learning models. So here's our setup and how we looked at this problem. So let's say you have an assembly line. And on that assembly line, you're trying to, say, weld 2 pieces of metal together as part of this process. It's more complicated than just saying, hey, machine learning model, is there a gap in that weld that was just done? Yes or no? Because I want to be able to make a decision on that and then check and then maybe try to weld it again. What if I try it 3 times and there's still a gap? Well, maybe that there's something defective going on. This also raises questions of how often should I pull the machine learning model? Because the machine learning model is on some camera that's then going into the logic. When is the appropriate time I should do that? So this work was all about practically how do I integrate the PyReason software, particularly the PyTorch tool set for deep learning. And what we designed was APIs that allowed these 2 things to communicate together and be able to set up based on the application, how often do they communicate? And once they once you get the results from a machine learning model, do you then need to run inference again? Because out of the inference might come a decision on what I should do next. But going along with that, like we saw earlier with reinforcement learning, the explainable trace is a key aspect of this. Because not only can I have control over this process, I can also analyze this more. And this trace, it's written as a table here because it can be treated like one. It can be analyzed by other algorithms to see, hey, are there trends in what's going on here? Are the logical rules I made around welding, do they make sense or not? Is it checking, is it always failing after 2 times and I'm waiting for 3? Well, I don't need to do that 3rd check maybe. Can I do this kind of analytics? Now, seeing this, though, makes you think about, okay, well, if I have these I have these machine learning models that are, perceiving things. And, they make mistakes of their own. And where machine learning models tend to make the most mistakes is when you put them in an environment that's different than their training data. And so if you do that, things are what are called out of distribution. But as humans, we are actually very good at recognizing things even when it's in a new distribution. But I don't think anyone in this room has ever saw me, walk around with a heavy winter jacket, but in a couple of months you probably will. And so you will still be able to recognize it's me, even though you had no prior history of seeing me every year after year wearing a winter jacket and boots. So how do we go about doing this with machine learning and logic together? Well, we set up a problem where here the project sponsor, they were really concerned. It's like, okay, let's say you have a bunch of machine learning models. And they're all maybe trained differently, but we don't know anything about how they work together. And we're going to put them in a new environment that is going to be different from what they were trained on. But maybe we grab the best of each one. And so in this example, we created the simulated data so we could control the distribution. We see that these two models are reporting a little bit different results as to what they detect, even in the same picture. So with respect to a psychological perspective, using multiple models actually mimics a lot about how we perceive things. Because we have a collection of autonomous systems that just respond to stimuli. And it tells us things like, hey, that shirt is blue. That wall is white. We just recognize these things. We can't explain them, but we can instantly recognize it. When we see something wrong, or that we think is wrong, we get a little bit of a cue that, hey, something is off here. So if you were to, right after this lecture, if you were to leave and go to Boston and walk down the street, and from a distance you see a man with a beard and a jacket and a tie like mine, you might think, oh, that's Paulo. But then you'll stop and think, no, that can't be him. He's back in Syracuse. So what you did there was you had a perception. Right, when we do this all the time, right? We always recognize people from a distance and then we think, no, that's not them. But the second step is interesting because what has happened is there's a higher order of cognition, the same kind of reasoning that we use when we do math problems, walks us through some logic as to why that perception is mistaken. And this is what we're trying to accomplish here. So here we use this idea of an abductive algorithm again. We have these machine learning models and they're all saying something different. And we have rules that we have learned about the model's prior performance, but that's only on the data that they've been trained on. It's nothing to do with how they interact. And then we have some simple domain knowledge, such as an object can't be a car and a tree at the same time. The abduction algorithm is designed to make sure that the final result is consistent with the domain knowledge, so we can't have any tree cars, and also minimize the number of these red flags that appear, such as, oh, that person is back in Syracuse and I'm now in Boston. And again, we frame this as a single optimization problem. And this is all done at test time. So there's no training data involved. All the models were pre-trained. But then the results of this optimization problem get converted back into what the output should be. And we compared this to the best single model, the average performance of all the models, even looking at the results of if you do like a majority vote over the models. And interestingly, the results were much better than any of those approaches. We're talking 10% better, sometimes more. And so this gave us some intuition that, hey, looking at how to combine these models, if you can approach it from this metacognitive standpoint, turns out you can do a lot better. So anyway, to conclude, the early work on annotated logic provides some insights into making, doing reasoning in an attractable way. And we built on that with lat logic by adding temporal extensions and adding this notion of absolute uncertainty that also gives some other advantages. So PyReason we created provides a robust implementation for a lot of different use cases, both modeling agents as well as interacting with machine learning models. And we have some ongoing work that I just described. So before I open up to questions, if you're interested in the kinds of things going on in the lab, in terms of like, if you're interested in positions, that is something that probably in the coming months we'll be releasing information on. With the lab, we call it the Leibniz lab. And it's basically because Leibniz, he has made contributions to both calculus, which underlies machine learning, and he's also made big contributions to logical proof, which underlies everything done in PyReason. And so in one person, you have both sides of the problem. And so, so if you're interested, you can check out the website. So open up to any questions you might have.